Inside a modern factory, the scale of the mechanical rhythm is impressive. Thousands of components move in perfect coordination to meet a production target. This environment relies on a rigorous administrative cycle. A system generates a work order, parts are staged, and a technician inspects the equipment before clearing the machine for service. But a quiet anomaly often hides in the maintenance logs. This exact task might be performed every 30 days, and every 30 days, the technician records the same result: no defect found. Over years of repetition, this high volume of activity can gradually be mistaken for evidence of its own necessity. Production rates, operating environments, and equipment age are constantly evolving. Yet in many plants, the maintenance interval remains entirely static. These schedules are often inherited from legacy systems. The earliest computerized management tools rigidly codified time-based intervals that were never intended to be permanent. These intervals frequently survive longer than the employees who first established them. We have reached a point where massive engineering ecosystems execute enormous amounts of labor based on unverified administrative defaults rather than physical evidence. Traditional maintenance is built on the belief that machinery wears out predictably with age. If we know when a part will fail, a calendar-based replacement should protect it. To test that belief, United Airlines commissioned a landmark study by engineers Nowlin and Heap. They investigated the failure patterns of hundreds of aircraft components. This chart shows what they actually discovered. Only 11% of equipment failures followed a predictable, age-related wear pattern. The remaining block, nearly 90% of all failures, showed no relationship to the calendar. These failures occurred randomly or immediately following a repair. Trusting a static schedule to prevent random failure is physically impossible. It creates an administrative burden without providing a reliability benefit. When a preventive task consistently yields a finding rate of less than 2%, it serves as a mathematical indicator of interval drift. The schedule has lost touch with the machine. This overmaintenance introduces a specific physical danger. Aviation research shows that an aircraft's failure risk spikes by over 33% in the hours immediately following a scheduled inspection. This is maintenance-induced infant mortality. Disassembling a perfectly healthy machine creates fresh openings for human error, misalignment, and contamination. Executing a perfectly scheduled inspection on a stable system manufactures a new vulnerability through the simple act of reassembly. Reliability engineers use a discipline called preventive maintenance optimization to realign these static schedules with the actual degradation rates of the equipment. A simple threshold for review is the 12-month finding check. If a recurring task has produced 0 corrective actions in a year, it is time to stop and question the interval. Realigning these intervals reallocates technician time from blind, calendar-based tasks toward monitoring the actual physical condition of the assets. Eliminating a task that lacks a technical basis reduces human error exposure while returning time to actual failure prevention. Looking back at the flawless facility from the opening, we can now see the impressive activity through the lens of interval drift. An entire operational ecosystem has volunteered itself to support one unverified tiny detail on a schedule. The most important inspection is the one directed at the schedule itself. Maintenance formally becomes waste the moment a schedule survives longer than the reason it was created. Most of us follow a simple logic when it comes to keeping machines running. Time dictates care. We change our car's oil every 3 months or 3,000 miles to keep the engine from wearing out. That exact same logic governs massive industrial facilities. On the first of the month, production lines halt, and technicians power down multi-million-dollar machines simply because the calendar says it is time for an inspection. A technician will crack open a gearbox, inspect a bearing, find absolutely nothing wrong, and bolt the casing right back up. 30 days later, that identical work order returns. The machine is stopped, the gearbox is opened, and the bearing is checked again, completely regardless of what was found the month prior. Do this often enough, and a dangerous illusion takes hold. Organizations start mistaking the sheer volume of their maintenance activity for proof that the work is actually necessary. A single monthly inspection that consistently finds 0 defects quietly burns thousands of dollars a year in wasted labor. Breaking the factory seal on healthy equipment actively invites problems. A microscopic speck of dust drifting into the casing introduces a brand new threat. Engineers call these maintenance-induced failures. Touching a perfectly fine component creates a fresh vulnerability. Following a strict preventive schedule doesn't guarantee reliability. In many cases, it is the exact mechanism that causes the equipment to fail. To understand how schedules get so detached from reality, you have to look at how they are built, usually starting with the original equipment manufacturer's manual. Those manuals are written for generic worst-case scenarios and warranty protection. The manufacturer has no idea how your specific factory operates, what your duty cycles are, or what environment the machine actually lives in. Once the machine is installed, the schedule begins to bloat. When a breakdown stops the line, management reacts by adding a new monthly inspection task to ensure it never happens again. This creates the sediment effect. New legacy rules pile on top of old ones, while obsolete tasks are never removed. What follows is interval drift. The machine evolves, but that bloated calendar schedule remains frozen. Maintenance becomes pure waste the moment a schedule survives longer than the physical evidence that originally justified its creation. The assumption that older machines are naturally more likely to break was tested rigorously in a 1978 aviation safety study by Nowlin and Heap. This chart breaks down the actual causes of equipment failure from their research. Only 11% actually follow the intuitive, age-related wear-out pattern, but a staggering 89% happen entirely randomly or immediately after a repair in a phase called infant mortality. Because nearly 9 out of 10 failures do not care what the calendar says, replacing parts on a rigid timeline does absolutely nothing to prevent them. In aviation, tearing down a perfectly running engine resets the infant mortality risk. You give human error a fresh chance to take down the system. Trying to beat the calendar is a mathematical trap. By intervening based on time, organizations are actively manufacturing their own breakdowns. You can start dismantling a bad schedule with a very simple diagnostic tool, the no-fault repetition check. Look through your work orders. If a recurring maintenance task has been performed for 12 straight months and found 0 defects, that interval is unconfirmed. The logic needs to be challenged. The modern replacement for the calendar is condition-based maintenance, or CBM. This demands that technicians stop asking what day it is and start asking what condition the machine is actually in. Today, we measure condition without touching the equipment. Vibration analysis, oil checks, and thermal imaging detect tiny fluctuations before a human eye ever could. Physical degradation becomes the only accepted trigger. You only pick up a wrench when the data proves the machine is starting to fail. The goal of modern operations is not to simply do less maintenance, but to stop worshiping the calendar. A true reliability culture reviews the logic of its schedule as fiercely as it inspects its machines, ensuring every turn of the wrench is driven by reality, not habit. Walk into any well-run utility room, and you will notice a quiet, orderly rhythm. Machines hum, shifts rotate, and scheduled maintenance runs exactly on time. But when was the last time anyone actually inspected the maintenance interval itself? The cycle feels comfortable. A scheduled work order opens on the first of the month. A technician inspects the equipment, finds no defects, and returns the machine to service seamlessly. Because that work order closes successfully every single month, the activity falsely becomes the evidence of its own necessity. We keep performing the task simply because the calendar says it is time. We are highly trained to manage visible mechanical problems. That hyper-focus often blinds us to the invisible assumptions quietly dictating our daily schedules. The National Institute of Standards and Technology outlines 3 distinct maintenance approaches. 2 of them are highly responsive: reactive maintenance, which is running a machine to failure, and predictive maintenance, which triggers work based on real-time condition data. Then there is the third approach, preventive maintenance. This method relies on static, rigid calendar dates, or operating cycles. But the factory floor is never static. Over time, machines age differently, production rates fluctuate, and operating environments continuously change. As that operational reality shifts, the original maintenance schedule remains untouched. The plan on paper becomes completely misaligned with the physical needs of the equipment. To test the logic of these rigid schedules, we can look to the landmark 1978 aviation reliability studies led by researchers Nowlin and Heap. This circle graph shows their core mathematical finding. Only 11% of equipment failures actually follow a predictable, age-related wear-out pattern. The remaining 89% occur completely at random or very early in an asset's life, regardless of its operational age. Because machines do not fail strictly by the calendar, a schedule alone is a mathematically flawed signal for deciding when maintenance is actually needed. You can think of it like a massive, beautifully maintained industrial utility system operating at a highly elevated capacity. Compressors run hot, heavy piping vibrates under stress, and multiple components actively overcompensate to maintain the facility's pressure. This systemic response consumes significant energy and labor to fix a problem it hasn't actually identified. But deep inside that system, on a remote branch line, there is a neglected, tiny quick connect fitting with a subtle, almost invisible leak. A massive, costly system response is driven entirely by a 1% local failure that remains unidentified. Organizations do the exact same thing with their maintenance schedules. We build massive, recurring labor routines around a single outdated assumption. Without an intervention, an entire maintenance department will willingly volunteer its resources to support a localized operational detail that was never questioned. Blindly following a misaligned schedule introduces a specific physical danger. Intrusive preventive tasks, like opening a gearbox or breaking a seal, create fresh openings for contamination and assembly errors. In these cases, the maintenance itself induces the failure. Aviation data bears this out. Research shows that an aircraft's accident or failure risk spikes 33.8% in the first hour immediately following an intrusive inspection. In fact, some of history's most catastrophic industrial incidents were driven in part by errors introduced during routine maintenance tasks. To spot interval drift before it wastes labor or induces a defect, you can run a no-fault repetition check. Isolate one recurring task on your schedule. Document how often the technician finds 0 defects, and then compare that history against the machine's actual failure data. A no defect found outcome does not automatically mean the task is a waste. Some inspections exist specifically to prevent severe, observable failures. Effective operations prioritize the quality of the evidence over the volume of the activity. The goal is to verify that the original schedule still has a documented reason to exist. Methodical. This visualization shows how a single 2-hour maintenance task, costing roughly $2,000 a year, accumulates into massive budgetary waste when multiplied across an entire facility. We are going to walk through a precise step-by-step audit to identify this exact type of waste using just one recurring maintenance task. The objective is to build a data-backed paper trail. If you reduce a task's frequency and the machine later breaks down, this documentation proves your decision was mathematically sound, removing the risk of personal blame. To execute this audit, you need 3 things: access to your maintenance software, 2 years of work order history, and 1 high-frequency maintenance task. Simply repeating a work order every month does not mean you are preventing a breakdown. It is time to inspect the schedule itself. Step 1 is to wall off the untouchable tasks. You must isolate and exclude any maintenance tied to safety regulations, environmental compliance, or protective devices. Cost reduction must never outrank compliance or safety. Those critical tasks require a completely different, highly regulated review process. Step 2 is the finding rate check. Pull the last 2 years of data for your selected task. Look at this stack of historical work orders. Every single one is closed with notes like satisfactory or no defect found. We use this data to calculate the PM finding rate. Simply divide the number of times the task actually found an actionable fault by the total number of times the task was performed. A healthy, optimized maintenance program generally finds a fault between 3 and 8% of the time. If your task's finding rate drops below 2%, you are over-inspecting the equipment. When a task yields 0 defects over an entire year, your organization is paying technicians to inspect a calendar, not protect an asset. Step 3 is to cross-reference your maintenance interval with the asset's actual breakdown history. You need to verify if the machine failed anyway, despite the scheduled maintenance. Many maintenance programs are built on the assumption that parts wear out on a predictable, age-based schedule. But as you can see here, components often break by snapping instantly under sudden stress, with no gradual warning. Researchers studying commercial aviation discovered 85% of equipment failures are entirely random, not tied to the age of the part. Opening healthy equipment on a rigid schedule introduces human errors, actively causing the next failure. The U.S. Navy validated this exact reality, using this data to completely eliminate extensive, time-directed overhauls on their fleets. NASA also adopted these reliability frameworks to prevent over-maintenance on their own critical systems. Look at this graph comparing failure probabilities. While traditional logic expects a curve where older parts fail more often, the reality for most components is a flat line. The risk of failure remains constant regardless of the operating age. Performing intrusive, calendar-based maintenance on random failure modes wastes your budget and actively induces new equipment failures. Step 4. The validation screen. Ask 3 strict questions. 1. Does it address a specific, credible failure mode? 2. Does the maintenance interval match reality? Checking monthly for a 3-year fault wastes labor. 3. Is there a better, non-intrusive option? If the task fails these questions, you move to Step 5, the substitution move. The safest way to eliminate a bad preventive maintenance task is to replace it, rather than just deleting it. Instead of tearing down a machine to inspect it, convert that calendar task into a condition-based check, like routine thermal imaging or vibration analysis. Finally, document this change in your software. Write a clear justification detailing exactly what was replaced and the historical data used to make the decision. This documented substitution aligns your maintenance schedule with actual physics. It protects the asset from unnecessary teardowns and protects your staff from misplaced blame. You have now successfully completed a no-fault repetition check and built a highly defensible paper trail. By executing this process, you free up technician capacity, eliminate the risk of maintenance-induced failures, and recover wasted budget. Your next step is to scale this approach. Identify 5 more recurring tasks with 0 findings this week and run them through this exact same screen. To achieve operational excellence, you must stop maintaining the calendar. Focus your resources exclusively on the actual, physical evidence of your equipment's health. Take a monthly preventative maintenance task that consumes 2 labor hours. At a fully loaded rate of $85 an hour, that single task costs over $2,000 a year. Multiply that across 40 similar assets, and you are burning over $80,000 annually on work that prevents nothing. Intrusive maintenance introduces physical risks alongside the labor costs. Every time you open a gearbox, break a flange, or disturb a bearing that is running perfectly fine, you create a fresh opening for contamination and assembly errors. Log into your facility's CMMS right now. Pick one recurring preventative maintenance task that you suspect is a complete waste of time. By following the next 4 steps, you will create a bulletproof, documented decision record to eliminate that task. You will remove the waste, and you will do it without taking on any personal blame if that machine breaks down in the future. Step 1. Before any technical analysis begins, your targeted task must pass a strict origin check. Some maintenance is not yours to cut. This includes environmental regulations, statutory tests, insurer conditions, warranty requirements, and anything protecting a safety-critical device. If your selected task falls into any of those categories, stop immediately. Those tasks require a completely separate, formal regulatory review. You can only proceed to the engineering review if the task is completely free of safety and compliance mandates. Cost never outranks safety. Skipping this origin screen is the fastest way to turn a well-intentioned efficiency effort into a catastrophic legal liability. Step 2. Pull the work order history for your selected asset, covering the last 12 to 24 months. Count the total times the task was performed and compare it against how many times an actionable defect was found. Do not confuse basic housekeeping with failure prevention. Tightening a loose guard bolt is not a defect that justifies an intrusive teardown. This plots failure probability on the vertical axis against operating age on the horizontal axis. Known as the bathtub curve, it illustrates infant mortality. Notice the massive spike on the far left representing early life failures, caused directly by unnecessary, intrusive maintenance on perfectly healthy components. If your task has yielded 0 real findings over an entire year, the maintenance team is not preventing failure. They are simply practicing their disassembly skills. Excessive maintenance drains the budget, and it engineers the exact breakdowns the preventive schedule was designed to stop. Step 3 interrogates the technical validity of the work. To earn its place on the calendar, your task must pass a 4-question screen. Question 1. Credibility and consequence. Does this specific failure mode actually happen to this asset in this exact operating environment? Question 2. Detection capability. Can the task actually detect the fault? A vague instruction to inspect general condition is technically incapable of finding a specific internal defect. Question 3. The physics of the interval. Performing a monthly physical inspection for a failure mode that takes 18 months to develop is pure theater. Question 4. Alternatives. Ask yourself if there is a way to use non-intrusive condition monitoring instead of tearing the equipment apart. If the task fails even one of these 4 questions, you must flag it for immediate elimination or substitution. Maintenance frequency is not evidence of maintenance quality. An interval must be supported by physics and engineering reality, not just habit. Step 4 formalizes the kill. You must build a paper trail so you never absorb the blame if the machine eventually fails from a separate issue. You achieve this using a 1-page decision record. This is the exact tool used to cleanly retire a preventative maintenance task. Fill out the form by documenting the historical evidence you just reviewed, and clearly state whether the decision is to eliminate, extend, or substitute the task. To finalize the document, you must obtain these 5 specific signatures. The safest way to structure this record is as a substitution. Instead of simply canceling an inspection, your record should show you traded an intrusive gearbox teardown for a non-invasive oil analysis route. A multi-signature file makes the decision a disciplined organizational choice. If a failure occurs later, the document proves a reasoned engineering call was made with the best available evidence. By completing these steps, you have successfully rescued labor hours, saved your budget, and minimized the risk of maintenance-induced failures. Take your completed decision record to your next planning meeting, secure the 5 signatures, and formally update your CMMS. True operational excellence begins when an organization stops measuring maintenance by volume and starts measuring it by relevance.
Welcome to this explainer. Let's just jump right into it. Today, we're unpacking a fascinating reality that is hiding in plain sight in almost every manufacturing plant and industrial operation out there. We're talking about operational waste. But not the obvious stuff, not scrapped parts or oil leaks or idle operators. We're looking at something totally invisible, heavily documented and, ironically, universally praised. We're going to break down exactly why your maintenance intervals themselves might just be one of the biggest sources of waste in your entire operation.
I mean, it sounds totally counterintuitive, doesn't it? Can doing a job perfectly actually be a complete waste of time? Let's say a tech gets a work order, walks out to the machine, checks every single box on the list flawlessly, and closes the ticket. Boom! We usually call that a massive win, right? We track it as schedule compliance, we give high fives, we celebrate it. But what if that task prevented absolutely nothing? What if simply completing scheduled maintenance is just creating this illusion of value while secretly burning through your labor and budget?
Okay, let's dive into this. There's a brilliant insight that really anchors this whole concept. Maintenance becomes waste when the schedule survives longer than the reason the schedule was created. Just think about that for a second. Over the years, a machine's reality changes. Production rates fluctuate, duty cycles shift, but the maintenance schedule, it often stays exactly the same as day one. The calendar-driven activity just gradually detaches from the actual physical condition of the equipment. We literally stop treating the machine, and we start treating the calendar.
And look, this leads us right into a deeply entrenched assumption we have in the industrial world. It's called the age reliability myth. For decades, we've had this gut-level belief that mechanical parts just naturally wear out predictably over time. The logic goes, reliability is directly tied to operating age, so the more often you overhaul a machine, the safer you are from failure. This is exactly why we rely on these rigid, unquestioned overhaul schedules. We assume replacing a part before its expiration date is a guaranteed win. But the actual data, it tells a completely different story.
Now, what's really interesting about this slide is what the data actually proves about how machines break. This comes from the famous Nolan and Heap study, which was originally done for the aviation industry. Check out that massive 89%. 89% of equipment failures happen completely randomly. That means they show constant or early life failure patterns. Only 11% of failures are genuinely age-related or show an increasing probability of failure as time goes on. So if almost 90% of your failures are random, a super rigid time-based schedule isn't even addressing how your equipment is actually failing. To really understand how to fix this, we've got to look at how NIST, the National Institute of Standards and Technology, classifies maintenance. They draw a hard line between preventive and predictive maintenance. Preventive uses fixed time or cycle-based triggers, like changing a filter every 90 days. The trigger is literally just the clock. Predictive maintenance, though, relies on observed reality.
It uses condition-based triggers like a sudden spike in vibration or temperature. Predictive works because it listens to the machine. Preventive often fails because it only listens to the calendar, completely ignoring the fact that the operating reality has changed. Let's put this into some visceral financial terms, because the costs here are wild. What does unnecessary preventative maintenance actually cost you? Let's take one basic monthly task that takes 2 hours. Say your fully loaded labor rate is $85 an hour. That's $2,040 a year for just one task on one asset. Multiply that across, say, 40 similar tasks that consistently produce 0 findings. You are literally burning over $80,000 every single year on work that prevents nothing. It's pure invisible overhead, draining your budget without moving the needle on reliability at all. And this pulls us straight into what we call the over-maintenance trap. You see, most maintenance programs just grow organically over time. A machine goes down, and a well-meaning manager adds a new weekly check just in case. Manufacturer recommendations are blindly copy-pasted into the system. But here's the kicker: nobody ever removes tasks. Over the years, these scheduled tasks just accumulate like sediment. They get thicker and heavier, eating up massive chunks of labor, spare parts, and planned downtime, all while your failure rates don't budge one bit. You're doing way more work, but you are not getting any more reliable.
But wait, actually, it gets worse. Overmaintenance isn't just a waste of money, it's legitimately dangerous. This is going to startle you. Aviation safety research shows that the risk of an aircraft failing or having an accident is 33.8% higher in the very first hour immediately following a scheduled inspection. Just let that sink in for a moment. The simple act of inspecting the equipment temporarily makes it significantly more likely to fail.
We actually have a formal term for this physical risk. It's called maintenance-induced failure. This happens when equipment failures are actively caused by the unnecessary maintenance activities we did to try and prevent them. Teardowns, intrusive inspections, you name it. And this isn't some rare fluke either. The ARC Advisory Group estimates that these self-inflicted errors account for somewhere between 30 and 55% of equipment failures in certain environments. When you tear apart perfectly healthy equipment just because the calendar told you to, you are playing a really dangerous game.
And this brilliantly illustrates exactly why overmaintenance is so hazardous. Think about it. Every single time you open a perfectly healthy gearbox, or break a flange, or mess with a bearing that was running flawlessly, you are opening the door to fresh disasters. You're introducing the risk of infant mortality from a brand new defective part. You're introducing human assembly errors. You might slightly misalign something or accidentally let dirt and contamination slip inside. You're essentially paying technicians to go out and actively inject risk into your highly stable systems.
Which brings us to this really stubborn pattern in our industry. I call it the invisible rule. The maintenance schedule is reviewed less often than the machine itself. The schedule just quietly acquires this permanent status. It's kind of like an old family recipe that nobody's allowed to alter. The engineer who wrote the original plan probably retired 10 years ago. The machine has been upgraded. Production demands have completely changed. But that schedule, it just keeps spitting out the exact same work orders, week after week, month after month.
So the crucial point is this absolute jaw-dropper of a statistic. In a lot of facilities, 20 to 35% of preventative maintenance tasks generate absolutely 0 findings. 0. The techs do the work, close the ticket, and report that everything is perfectly fine, month after month, year after year. And look, a finding rate that low is not a sign that your maintenance is perfect. It is a massive, flashing red warning light that your intervals have completely lost touch with reality and your highly skilled technicians are just wasting their valuable time.
So how do we actually measure this? We use something called the PM finding rate. It's this incredibly useful, actionable diagnostic metric that tells you straight up if your intervals make sense. If your tasks are uncovering actual issues 3 to 8% of the time, congratulations, you've got a mature, optimal program. If you're finding problems more than 10% of the time, your intervals are too long and you need to inspect more frequently. But if your finding rate is under 2%, that is mathematical proof of over-inspection and wasted labor. You're simply looking too often at things that aren't breaking.
The great thing is, you have a really concrete way to hunt down this waste in your operation right now. It's called the no-fault repetition check. Here's what you do. Go into your system, pull up a recurring preventive task, count how many times it was done last year, and then tally up how many times the tech found no defect. Then, hold that interval up against the actual failure history and the machine's current reality. If the machine never breaks, and you literally never find anything during the inspection, well, your interval is just wrong.
Let's move to our options and see how this builds into an actual strategy. When you spot a task that hasn't produced a single finding in 12 months, you've got 3 valid evidence-based moves. Number 1, extend the interval. If a monthly check finds nothing, push it to quarterly. Number 2, simplify the task. Stop the intrusive teardowns and switch to condition-based checks. Think thermal imaging or vibration analysis. Or, number 3, just eliminate the task entirely if the inspection literally produces no actionable outcome.
As we wrap up this explainer, I really want to make sure this core paradigm shift hits home. The goal here is absolutely not to just do less maintenance to save a quick buck. That's a reactive trap, and it'll catch up with you. The true goal is to demand that every single maintenance action still has a valid, evidence-based reason to exist. We have to stop just cheering for the sheer volume of maintenance we complete and start fiercely protecting the relevance of the maintenance we perform. I'm going to leave you with this final, provocative thought to chew on. Look at your own facility, your team, your daily boards. What recurring task in your operation only survives right now simply because it's always been there? Because if you can't point to the actual evidence that justifies that interval, it is time to seriously question that schedule. Thanks so much for joining me in this explainer. Now go out there, ask some hard questions, and reclaim your time.
Okay, I want you to really let this quote sink in for a second. A task can be completed perfectly and still be unnecessary. In the world of industrial operations, we spend so much time optimizing, right? We track how fast our technicians can turn a wrench, how quickly they close out a work order, and whether the paperwork is absolutely spotless. But how often do we actually stop and ask, hey, did they even need to turn that wrench in the first place? And that brings us to the core question we really need to answer. When does preventative maintenance stop preventing and start repeating? I mean, this is a scenario that plays out in facilities literally all over the world every single day. A work order pops up, a technician goes out to inspect a machine, they find absolutely nothing wrong, they close the ticket, and the equipment goes right back to work. And then next month, that exact same task pops up on the calendar all over again. Over time, just the pure act of doing the maintenance becomes the only proof that it's supposedly necessary. Welcome to the Explainer. Today, we are tackling this issue head-on, focusing specifically on how to identify maintenance waste. We're going to dig into the source data to uncover the proven strategies you need to stop over-maintaining your equipment. We'll completely shift how we look at maintenance schedules and find that hidden waste that's quietly draining your budget and your team's valuable time. So let's take a quick look at our roadmap. We'll start with the over-maintenance trap. Then we'll break down a huge industry myth called the age reliability fallacy. Next, we'll get into the actual metrics for identifying maintenance waste, followed by fixing inventory data waste. And finally, we will talk about how to kill bad PMs. All right, let's jump right into section 1, the over-maintenance trap, when safe becomes sorry. So there is this very common, very natural assumption in asset management that doing more maintenance automatically means you're going to get better reliability. The whole better safe than sorry approach, right? When in doubt, grease it, check it, rebuild it. But when you actually look at the data, that instinct isn't just a little bit off, it is actively harming operations. Take this $80,000 figure. That represents the annual cost of just one unnecessary preventative maintenance task when you apply it across a whole fleet. Let's do the math real quick. Say you have a monthly PM that takes 2 labor hours. At a fully loaded rate of $85 an hour, that's over $2,000 a year just for a single machine. If you multiply that across 40 similar assets in your plant, you are burning over $80,000 every single year on a routine that is catching 0 defects. But the financial cost is really just the tip of the iceberg. The true hidden cost of a bad PM is that it can actually cause your equipment to fail. This is a concept called infant mortality. When you do intrusive maintenance, meaning you're opening a gearbox, breaking a seal, or taking apart a bearing that was running completely fine, you are literally creating a fresh opportunity for human error. You introduce the risk of dirt getting in there, misalignment, or just putting it back together wrong. In the reliability world, we call this a maintenance-induced failure. Now, if you think I'm exaggerating, just look at aviation. Aviation safety researchers have studied this to death, and they found that an aircraft's risk of failure is actually 33.8% higher in the very first hour right after a scheduled inspection. 33.8%. The actual act of pulling those panels off and poking around made the plane statistically more dangerous to fly because of the defects they might have accidentally introduced. Basically, sometimes the absolute best thing you can do for a healthy machine is just step away and leave it alone. Moving on to section 2, the age reliability fallacy, myth versus reality. So why do we keep doing all these intrusive, wasteful checks? Well, it mostly comes down to a psychological trap and a really outdated assumption about how machines actually break. The
traditional belief, and honestly this makes perfect intuitive sense to most of us, is that machines just wear out over time. We assume that as a part gets older, its chance of breaking goes up. So logically, if we replace it on a strict calendar schedule, we beat the failure, right? Well, back in 1978, two researchers, F. Stanley Nolan and Howard F. Heap, dug into airline data and discovered something that totally flipped the industry on its head. Most failures are actually random, and they have absolutely nothing to do with the equipment's age. Check this out. Their findings show that a massive 85% of component failures are just totally random. They happen because of a power surge, operator error, bad raw materials, things like that. Only about 15% actually follow that predictable age-related wear-out curve, where swapping parts out on a schedule makes sense. To put that in perspective, for 85% of your equipment, scheduling a calendar-based overhaul is basically useless. You're trying to fix a completely random problem with a rigid fixed schedule. Okay, let's get into section 3, identifying maintenance waste. The data. It's one thing to say calendar-based maintenance is flawed in theory, but how do you actually spot this waste on your own factory floor? You've got to look at the hard data. The golden metric you absolutely need to track is your PM finding rate. This is just the percentage of your preventative work orders that actually find a defect you need to fix. Now, a healthy, optimized maintenance program usually sits between 3 and 8%. That means your inspections are doing their job, catching problems before everything grinds to a halt. But if your finding rate drops below 2%, that is mathematical proof that you are over-inspecting. Your team is spending all their time just confirming that the equipment is perfectly fine. The core problem boils down to this. The calendar schedule usually survives a lot longer than the reason it was ever created in the first place. Think about it. Your operating conditions change, you upgrade parts, production shifts, but that maintenance interval, it might stay exactly the same for 20 years. If you got a recurring task that has produced absolutely zero findings and zero corrective actions for an entire year, you're experiencing interval drift. Your machines have moved on, but your schedule is totally stuck in the past. Which brings us to section 4, fixing inventory data waste. MRO cleanup. You know, self-inflicted waste doesn't just live in the maintenance schedule. It thrives in the storeroom, too. Your MRO, maintenance, repair, and operations, inventory databases are often a goldmine for savings, and you don't even have to touch a wrench to find them. A ton of this waste comes from really messy master data. We're talking duplicate part numbers, super vague descriptions, and zero manufacturer cross-references. Because of this, it's incredibly common for storerooms to carry 30 to 50% excess inventory. Imagine you stock a standard AC contactor, but because of bad data entry, it's sitting in your system under 3 different OEM part numbers. You are literally paying 3 times the carrying costs, and worse, you'll still get rush orders when one version runs out, while the exact same part is sitting just one shelf over. And man, when you scale this across multiple facilities, the waste just explodes. Imagine Plant A is having weekly stockouts of sensor X, shutting down their lines. Meanwhile, Plant B has a massive pile of that exact same sensor just gathering dust, but they have it listed under a completely different part number. There's zero visibility. By just cleaning up those descriptions and getting everyone onto a centralized database, facilities can regularly slash their inventory by 20 to 30% in just 90 days. And the best part? It is totally risk-free. Finally, let's look at section 5, how to kill bad PMs without getting blamed. So, spotting a useless task is actually the easy part. Pulling it off the schedule without causing a massive panic, that's the real trick. You have to acknowledge the office politics here. There's a great saying, nobody ever got fired for doing a PM, but plenty of people got blamed for canceling one. And that totally hits the nail on the head. If you just go rogue and delete a bunch of PMs and a machine happens to break down a week later, well, everyone's going to point the finger at you, even if the PM wouldn't have caught the problem anyway. You have to be strategic. The way you overcome that fear is by building an airtight paper trail. We call it a no-fault repetition check. Step 1, build the failure data file. Pull the history and definitively prove that this task has literally never caught a failure. Step 2, test the task against the failure mode. Ask your technicians, hey, can this visual inspection actually detect an internal bearing defect? Usually, the answer is a hard no. And step 3, replace it. The absolute safest way to kill a bad calendar-based task is to swap it for a targeted condition-based sensor route, things like vibration or oil analysis. You aren't cutting corners, you're upgrading how you detect problems. Now, quick pause here. This is absolutely critical before you go auditing your schedules. Cost never outranks safety or compliance, ever. If a PM task is a regulatory requirement, a statutory test, an environmental check, or an inspection for a safety device, it needs a completely separate formal review. You simply cannot casually cut safety-mandated tasks, no matter how rare the findings are. Remember, we are hunting for operational waste, not putting safety on the chopping block. Well, we've covered a ton of ground today, from dismantling the age reliability fallacy to totally cleaning up inventory waste. So I want to leave you with one final provocative question to think about. What recurring activity in your operation survives mostly just because it has always existed? I challenge you to go back to your facility, open up your maintenance schedule, and start asking for real evidence behind those intervals. Demand the data, not just the habit. Because at the end of the day, the best maintenance program isn't the one doing the most work, it's the one doing the right work at the exact right time. Thanks for joining me for this explainer, and keep asking those tough questions.
Welcome to this explainer. Today we're going to challenge a pretty universal operational belief and totally shift how you think about equipment wear and tear. I mean, if you've ever looked at an aging machine on the floor and thought, well, it's getting old, it's probably going to break down soon, I completely get it. I used to think the exact same thing. It's just human nature, right? We link age with failure because we see it everywhere in our daily lives. But what if the hard data tells a completely different story? Today we are busting a massive maintenance myth and really diving into the 6 common failure patterns to reshape how we approach reliability. Okay, let's just dive right in by asking a genuinely tough question. Could our comfortable, calendar-based maintenance schedules actually be causing more failures than they prevent? Think about it. In so many operations, we tend to view maintenance frequency as direct proof of maintenance quality. The mindset is kind of like, hey, the more often we check it or rebuild it, the safer it is, right? But we really have to stop and ask ourselves, when exactly does a perfectly executed preventative maintenance task stop actually preventing a breakdown and just devolve into a repeated habit?
We naturally assume that parts fail just because they get old. And honestly, on the surface, that makes perfect sense. Our bodies age, our clothes wear out, our cars get rusty. But major industrial data proves this assumption is mathematically wrong when we look at complex multi-part systems. The old belief assumes this nice, predictable relationship between a machine's operating age and its reliability. The reality, though, it's way more surprising. It turns out that most failures in complex equipment are completely random, literally entirely disconnected from the sheer passage of time. So the real turning point for busting this myth was this landmark 1978 aviation study by researchers Nolan and Heap. This study shockingly revealed that up to 89% of failures are entirely random, not age-related at all. This was an absolute game changer. It fundamentally revolutionized commercial aviation maintenance and made flying exponentially safer by letting data drive the schedule. And look, their findings weren't just some crazy fluke. This research was later heavily backed up by Swedish researchers and even the US Navy. Across the board, no matter the industry, the data settles into a pretty stark reality. Roughly 85% of equipment failures fall into a random category, while only about 15% are genuinely age-related. To really understand why age doesn't always equal failure, we have to look closely at the 6 distinct failure patterns. Researchers have validated these across aviation, naval, and modern manufacturing sectors. You'll hear these famously referred to as patterns A through F. By tracking exactly how the probability of a breakdown shifts over a component's lifespan, we can neatly group these 6 patterns into 2 very distinct categories, and that is going to dictate exactly how we should treat them.
All right, let's group these into our 2 main buckets. First up, we have the age-related failures. In this category, the probability of a component breaking down actually does predictably increase with time. This bucket holds patterns A, B, and C. Now here's the kicker. This first bucket only accounts for about 15% of all components. Just 15. If a specific part falls into one of these 3 patterns, then yeah, having a strict calendar-based replacement schedule makes perfect sense because we know exactly when it's going to get dangerous. Let's break those down. Pattern A is the classic bathtub curve. You've probably heard of this one before. It's really common in components like sleeve bearings that have early bedding-in problems. Basically, the parts are just getting used to running together, which causes a pretty high failure rate right at the very beginning. We call this infant mortality. But once the component survives that phase, it enters a long, stable, useful life before finally hitting an increasing wear-out zone way toward the end as the physical materials simply start to degrade.
Next up is pattern B, also known as the wear-out curve. Unlike the bathtub curve, you really don't have to worry about those day 1 bedding-in failures here. Think of items like bronze bushes. They tend to operate flawlessly with a super stable, low level of random failures for a long, long time. But as they reach a certain age, shaft clearances increase and the physical wear accelerates incredibly rapidly, which creates a massive, sharp spike in failure probability. For pattern B, replacing the component right before this sharp spike hits is an excellent, highly cost-effective strategy.
Then we have pattern C, which is pure fatigue. So instead of a sudden, sharp spike in breakdowns, picture this as a constant, steady climb in failure risk as the component ages. It's really common in parts that are subjected to heavy cyclical loads, gear teeth, metal springs, or drive shafts. Because there's no sudden jump, just that continuous upward climb, the maintenance strategy here is to simply replace the item once the probability of failure reaches a level that becomes mathematically unacceptable for your specific operation.
Now this next part, this is where the data completely flipped my understanding. Let's move into our second bucket, the random failures. This bucket surprisingly represents the vast majority of industrial equipment out there, capturing patterns D, E, and F. For these components, failures are absolutely not neatly tied to the calendar. And because this bucket accounts for a massive 85% of complex components, it literally forces us to completely rethink the traditional way we do time-based maintenance.
Let's start with pattern D, the break-in curve. With this one, you have a very low failure probability when the item is brand new out of the box. That risk rises pretty early on, but then, and this is the absolutely crucial part, it flattens out and settles at a constant conditional probability for the remainder of the component's life. So, in plain English, once it survives that initial break-in period, getting older doesn't make it any more likely to break. Its failure risk just plateaus and stays there forever. Moving on to pattern E, which is completely random throughout its entire life cycle. The probability of failure here is just a flat, horizontal line from day one. There's absolutely no optimum calendar time to change this component, because pulling it out and replacing it won't improve your reliability one single bit. A perfect way to picture this is a car tire hitting a nail on the highway, or a solid-state memory chip that works flawlessly until a totally random electrical fault occurs. The calendar has absolutely zero impact on these events. Finally, we have pattern F, the infant mortality curve. And wow, this one is incredibly important to grasp. It's typical of complex equipment, where the absolute highest risk of failure is right after it's first assembled, overhauled, or repaired. Once it survives its initial bedding-in period, it drops down and settles into a constant, low-level random failure rate. Going back to that famous Nolan and Heap aviation study, I was completely blown away to learn that a staggering 68% of components followed this exact pattern.
And that leads us to this astonishing realization. Over-maintaining complex machinery can actually do much more harm than good. In many cases, scheduled overhauls will actively increase your overall failure rate. Just think about it for a second. If 68% of your equipment follows pattern F, and you go in and tear apart a perfectly stable, smoothly running machine just because the calendar says it's time for an annual overhaul, you are artificially reintroducing that high early risk of failure back into a stable system. Human error during reassembly, defective new parts, or even simple misalignments can suddenly crash a machine that was doing just fine. This dynamic perfectly illustrates the danger here. If a part is even slightly misaligned during reassembly, its useful life plummets dramatically. It's not the sheer passage of time that's killing the component, it is the physical operational stress of being put back together slightly off-center. A tiny, almost invisible local misalignment introduces friction and vibration that will destroy a system far faster than a calendar year ever could. It proves that how a machine is running matters so much more than how old it is. All of this brings us to a really pervasive operational phenomenon called maintenance interval drift. Basically, if we rely strictly on the calendar, the schedule itself often survives much longer than the evidence that originally created it. Over the years, the machine itself gets upgraded, the duty cycle shifts, production speeds change, but that old maintenance schedule, it just sits there, quietly acquiring permanent, unquestioned status in the system. The machine's output is scrutinized daily, but the logic behind when we take it offline for maintenance is rarely ever challenged. When we ignore this drift, we end up totally trapped. Think about how often a work order is opened. A complex task is performed perfectly by your team. The machine goes back online and absolutely nothing was found wrong in the first place. But the exact same task just returns next month anyway. That isn't prevention, that's just a repeated habit, and quite frankly, it is wasted maintenance. Evidence-based maintenance, on the other hand, completely shifts the focus. It uses observed, real-time operating conditions like vibration anomalies or temperature spikes to trigger a response rather than just blindly flipping a calendar page. So, how do you bust this myth in your own facility? Try this simple 30-minute diagnostic check today to see if your maintenance intervals actually still make sense. It's called the no-fault repetition check, and it's incredibly straightforward. Pick one recurring preventative task you've done at least half a dozen times this past year, and ask yourself, how many times did we find 0 defects? Compare that number against the actual failure history of the machine, and verify if the original reasoning for that schedule still holds up. If the data doesn't support the interval, well, it's definitely time for a better conversation.
I want to leave you with this provocative thought to take back to your team today. Are you managing actual equipment conditions, or are you just managing the calendar? Remember, the most useful maintenance interval is not the oldest one. It is the one still supported by hard evidence. Stop letting an outdated schedule dictate your operational reality. Thanks for joining me on this explainer, and I really hope this helps you look at your next maintenance work order in a completely different, much more critical light.